10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff. We have liftoff.
When it's my life on the line, what type of a team do I want out there holding it in their palm? And the answer I came to is, I think, the identical answer you would come to in the identical circumstance. When your life is on the line, you're going to want a team that's the best holding it in their palm. And how do teams get to be the best? They get there by practicing fundamentals, by doing little things consistently and religiously day in and day out until they become as natural as breathing. You don't even think about them. Now, there's lots of fundamentals out there, but there are three that I think have overarching importance to the success and safety of all teams everywhere, and those are the three that I want to talk about this morning. When I'm involved with any team, but particularly when there are lethal consequences associated with the team environment, as there are with you in firefighting and emergency response, just as it is in the space program. People die when they don't understand the dangers of a normalization of deviance and protect themselves against that. And I'm going to talk about that. I'll define that here for you in just a moment. I want everybody on the team understanding the essence of responsibility as it applies to the individual as well as it applies to the leadership. And I want a team that's filled with courageous self-leaders. I think Harold really kind of hit on that in his earlier comments. It's self-leadership that determines how safe and successful you can be. It's looking deep inside yourself. It has to be everybody practicing self-leadership for the team to succeed. It can't be 99 out of 100. Every individual, again, particularly in hazardous environments, has to be a courageous self-leader. So I'll talk about that as part of this teamwork program. Now, I'm going to use some experiences I had both as an Air Force flyer and as a NASA astronaut to develop some points on these fundamentals. And sadly, NASA provides me with two great tragedies to draw from to make some points. Those tragedies being the Challenger disaster and the Columbia disaster. So I imagine most of you are probably foggy in your memories what caused the Challenger to be lost. And because I will be referencing that program, referencing that disaster in this program, I want to take a moment to briefly review for you mechanically what caused the loss of the Space Shuttle Challenger. Challenger was a failure of the right-hand solid rocket booster. These things are so big, they're 150 feet long, 12 feet in diameter, and each of them weighs 1.3 million pounds. They're too big to be made in one piece at the factory in Utah and shipped in one piece down to Florida, where they're launched. So they build them in 4 propellant-filled pieces that are shipped separately by flatbed rail car from the Thiokol plant in Utah down to the vertical assembly building at Cape Kennedy. There, these segments are stacked on top of each other to form twin towers of boosters. The gas tank is hung between the boosters. The wing vehicle is attached to the gas tank, and then all of this is taken out to the launch pad on this 9 million pound mobile launch platform. Now, when these boosters ignite, they burn at 5,000 degrees Fahrenheit and at a pressure of about 1,000 psi. Steel boils at 5,000 degrees. So you have to ensure in your design that the steel of the booster is never touched by the fire that it contains. So there's insulating material to run the inside length of these segments. The obvious weak point in this design is where you've bolted these segments together, because there you have a potential leak path for the gas to pass to the outside, melt the steel, and cause a catastrophe. Now, I'm not going to go into the engineering specifics of the joint design that was intended to prevent such gas leakage, other than to say it was based on a redundant flexible O-ring scheme. 2 flexible O-rings. Here's a piece of one of them right here. 12 foot in diameter at each perimeter of those segment joints. 2 of them at each joint were supposed to form a redundant steel-to-steel pressure seal to prevent the fire from leaking out. On Challenger, both O-rings failed on the bottom segment of the right side solid rocket booster. Here's Challenger coming off the launch pad. In that yellow area, you'll see a black smoke being ejected. That's the vaporized O-rings being shoved out that bottom joint. You now have 5,000 degrees eating into that outer wall. As the rocket flies higher, the gas is vaporizing a bigger and bigger hole in the side of the booster rocket. 73 seconds into flight, the rocket comes apart, killing the 7 astronauts. Now, what you're seeing here appears to be an explosion, but was not. This was a catastrophic structural breakup. The fire weakened the attachment to the bottom of the gas tank. That bottom just basically fell off. The top of the booster rotated into the top of the gas tank, rupturing that, and under the aerodynamic and G-loads of the moment, the vehicle just shredded itself. Nothing detonated, nothing blew up. That will become important to remember downstream when we talk about crew survivability associated with this tragedy. Now, you're going to need that background to understand some of my downstream comments, and certainly you're going to need it to understand my comments about normalization of deviance. What is this? Well, it's that natural human tendency, particularly in pressure circumstances, to want to take shortcuts, to accept a lower standard of performance. Maybe it's a lower standard of personal performance, a lower standard of performance for some team you lead, lower standard of performance for some machine firefighting equipment that you oversee. But it's very human to find yourself in pressure circumstances, and God knows you folks find it on every call. Very human to find yourself in a pressure circumstance and rationalize, I can't execute to meet these standards I've been trained to meet. I'm going to have to take a shortcut. Maybe the shortcut is what Harold was talking about, not doing a proper risk assessment. Maybe it's not having the right communication in place. Maybe it's not wearing the right protective equipment, whatever. But it's very human in pressure to rationalize, I can't do this job and meet the standards. I'm going to have to take a shortcut. And so you take that shortcut, and guess what the consequences are? There are no bad consequences. You aren't injured. Nobody's injured. The emergency response proceeds successfully. There are no bad consequences to your actions in taking that shortcut. What's that going to do? It's going to loop it back into your brain and reinforce the rightness of that earlier decision to take the shortcut in the first place. So what's liable to happen the very next time you find yourself in these same pressure circumstances? And I guarantee there's going to be a next time, particularly in your businesses. Because there were no bad consequences the last time you took the shortcut, you're going to be mightily tempted to do it again. You do it enough times, and what happens? The shortcut becomes the norm. Here are the standards that you're expected to be meeting. Here's where you are in execution. This deviance is invisible to you. You don't even think about it. It has become normalized into your actions, into your team actions. And what happens with normalization of deviance, it leads to predictable surprises. And if you ever want, and I'll tell you, in hazardous environments, predictable surprises on the job can be injurious and they can be deadly. If you ever want an object lesson in what normalization of deviance can do, a predictable surprise, look at Challenger. Challenger was no accident. Challenger was a predictable surprise. At the time that rocket came apart, scattered throughout NASA under contractors and filing cabinets and desk drawers were written documents, memos, predicting that the exact thing that did happen, i.e. failure of this O-ring, was going to happen. And where did people get the information to make such predictions? From the best source available, flight data. It doesn't get any better than to get the piece back and see how it performed. And that's the case with these solid rocket boosters. They're not throwaway items. 25 miles up, they burn out, they're jettisoned, they have gigantic parachutes that are deployed. These things are lowered into the water. Air is trapped inside them when they hit, so they float. Tugboats are positioned out there to put a line on them, tow them back to shore. There they're cleaned up, taken apart, inspected, and used over again. The operative word in this process is inspected. And on 14 of 24 flights before Challenger, Challenger was number 25. On 14 of 24 flights before Challenger, in the inspection process, quality assurance and safety people noted that the O-rings, which were never designed to be touched by fire, were being touched by fire. And they understood the ramifications of their findings. This design is flawed. It's going to fail. People are going to die. And they basically put words to that effect in these various memos. I want to share with you excerpts of two of these memos, both of which were written by Thicol engineers, the contractor, to their customer, NASA. The first memo is dated February of '84. This is 2 years before Challenger. And in part, the memo reads, the recent experience of two burned O-rings on STS-11, that's the 11th shuttle mission, raises concerns with STS-13. You know, when I read this, I wonder how come nobody was concerned about STS-12, my first mission. But apparently they weren't. The O-ring leak check procedure is also an urgent concern. Your support in this urgent matter is requested. 2 years before Challenger, the label urgent has been hung on this O-ring design. It's not working. Here's a sentence out of a Thicol memo dated July of '85. This is 6 months before Challenger. The memo was written by Mr. Roger Bougielet, a Thicol rocket engineer. In his memo, he wrote a very prophetic sentence. Here it is. It is my honest and very real fear that if we do not take immediate action to dedicate a team to solve the problem with the field joint, and that's the O-ring, having the #1 priority, then we stand in jeopardy of losing a flight, a crew, and all the launch pad facilities. Mr. Bourgelat's prediction was only off 73 seconds. He thought the rocket was going to blow up on the launch pad, destroy the vehicle, kill the crew, and take out the launch pad facilities. He missed it by 73 seconds. Challenger was no accident. Challenger was a predictable surprise. Now, I know what everybody's thinking right now. Why didn't the team react to these warnings, ground the fleet, and fix the problem? And the answer is, to a significant degree, the team was laboring under a long-term normalization of deviance. And let me explain. Approximately a decade before Challenger, a standard of performance was established for these O-rings in our failure modes and effects analysis document. They were given a criticality 1 label, meaning if they ever fail, it's loss of the vehicle and death to the crew. So a standard of performance was established for these O-rings. They can never show any hint of a failure mode. If they fail, it's death. And de facto, you have now established a standard of performance on how the team should react if they ever see a problem with the O-rings. Criticality 1 deviance, only one thing you can do, ground the fleet. But that standard of performance was established, as I said, about a decade before Challenger in a no-pressure situation. Emphasis on those words. When the first O-ring damage is seen, it's not a no-pressure situation. First O-ring damage is seen when they get the boosters back from the second shuttle mission. Now here you have leadership, quality assurance, safety people staring at their worst nightmare, evidence of a major design flaw in this multi-billion-dollar program. And they can see how the standard of performance has been violated. This is a criticality 1 deviance we're looking at, a burned O-ring. And at that point, the standard for the team was what? Ground the fleet. You cannot fly with a criticality 1 deviance. But the team could not bring themselves to adhere to that standard of performance established those many years earlier. Why? Because it's not a no-pressure situation. These people are under tremendous pressure, not just to see the fleet continue to fly, but to rapidly expand the shuttle flight rate. It's laughable now to hear, folks, but you know where we were headed in the early 80s with the shuttle flight rate? 26 missions a year. A shuttle was going to be flying every 2 weeks. And in fact, the shuttle made no economic sense if it wasn't flying at that flight rate. NASA had promised Congress and the American public the shuttle would dramatically reduce the cost of operating in space because it was going to be so easy to turn between missions. It would just take a couple weeks from landing to get it back on the launch pad with new boosters, new gas tank, new payload, and it's ready to go again. And that business model, 26 missions a year, became our God. Nothing could get in the way of that schedule. So now the team is facing a criticality 1 deviance. They have a standard of performance that they're supposed to adhere to, ground the fleet. But under this tremendous pressure, they start rationalizing why they can continue to fly or how to take a shortcut, to accept a lower standard of performance. What they do is they take a pristine O-ring. They intentionally damage it to a degree greater than what they saw in the damaged recovered O-ring. They put that intentionally damaged O-ring in a laboratory pressure test article. They pressurized it to 3,000 psi, 3 times the pressure it would ever see in flight, and that damaged O-ring held pressure. So the team rationalized, hey, even a damaged O-ring is holding pressure, and in flight the backup O-ring held pressure, so we don't need to ground the fleet. We can make some minor assembly processes and hope that fixes the problem, collect some data on the fly. We can continue flight operations in spite of a criticality 1 deviance. So they take the shortcut. And while I'm telling this story, I hope all of you are thinking about how many times you have rationalized. We're all human, we all come under pressure. How many times have you rationalized it's okay to take the shortcut? So now here the NASA team has rationalized it's okay to take the shortcut. You know, what they've done here now is accepted something that was never expected. It wasn't that the O-rings were designed to take damage and continue to function. They were never to see damage. But in this pressure cooker, the team has rationalized why it's okay to see some damage, something that's not expected and not understood. And flight operations continue. And guess what the consequences are? There are no bad consequences. The next couple missions return pristine O-ring, boosters that show pristine O-rings. And every time they break apart one of those boosters, see those perfect O-rings, what's that doing? Looping back into the brains of the NASA team, it was okay to take the shortcut in the first place. Then they get the boosters back from the 6th shuttle mission. They see more damaged O-rings. What happens now? We're deeper into the program. The expectations are higher. The promises have been made are greater. Harder now to go back to that original standard of performance that says ground the fleet. And now they have that history of having gotten away with in the past. It becomes a little bit easier to rationalize why it's okay to continue flight operations again. So they make some more minor assembly process changes and continue flight operations. Basically what's happening here, folks, is the damage seen on Flight 2 is slowly becoming the umbrella. And the team slowly starts rationalizing, as long as we never see damage that exceeds what we saw on Flight 2, it's okay to continue flight operations. Well, for another dozen times or so, they get back boosters where the damage to the O-rings doesn't exceed what they saw on Flight 2, until on Flight 25, Challenger's mission, the damage exceeds in a great way what they saw on Flight 2. Total primary and backup O-ring failure, loss of the vehicle, and the death of 7 astronauts. Basically, by the time Challenger was occurring, a large body of the team that was working this O-ring problem had come to expect to see O-ring damage. Now, I want you to think about that. We'd gone from something we correctly defined as intolerable to accept to something over 4 years and 24 missions has become what? Expected. Normalization of deviance. It is a killer of teams, folks. Literally, in hazardous environments, it will kill people.